Hello my friends of Water Labs, my name is Saul Montoya. Welcome to this tutorial. This tutorial is about hydrogeological speciation modeling with Phreeqc and the analysis with Julia. Okay? If you don't know about Julia, maybe this will be the first time that we introduce this amazing and promising programming language. Okay, you're going to receive this folder on the description of the video where we are going to run the first exercise of the Trixie documentation. Okay, and then we are going to do the analysis in a Jupyter notebook, but running a Julia kernel. Okay, so let's start with Anaconda. Okay, what you need to do is you need to download from the Phreeqc, you need to download the batch version of Phreeqc for your operating system. Okay, once you have downloaded, we are going to use Anaconda prompt. Okay, and then here I change it to my documents, change it to the okay, and then I run a Jupyter Lab. Okay, wait. Okay. How do we run Phreeqc on a Jupyter Lab? This is not so complicated. Why is not so complicated? Because what we need to do is we need to launch a terminal. Okay, if you have installed Phreeqc, actually Phreeqc is executable that you can call it from anywhere on your Windows operating system, on the DOS I guess. So if I type it Phreeqc, voilà. Okay, I can call it. Okay, but I need to change it to CD model dir, where actually I get the exercise 1, that is the file of the model. This is exercise out, that is the out model, but I'm going to delete it because I want you to see that we can do the whole run. Okay, so actually if I clear this, okay, so actually there is only exercise 1 here, and to run Phreeqc is very simple. Let's do an analysis of the exercise 1. The exercise 1, if you go to the Phreeqc documentation, is the speciation analysis of seawater, okay, with some uranium species. Okay, so here we have the pH, the density, temperature, the elements, and also some ions of uranium. Okay, and some reactions as well, because actually I mean on the documentation they say that these reactions are on the database, but they wanted to put these reactions here in order to prove that this is working. Okay. Okay, so you create a solution, you create the master species, the solution species, and the phases, because actually this is the unary need. I think it's something that can be precipitated. Okay. Okay, great. So actually you don't need to do much more. I mean, this is the exercise 1. If you want to see everything about the exercise 1, go to the Phreeqc documentation. But here, what I need to do is just I have to call it Phreeqc. I don't know if it's okay. I want you to see, so I will change it to Jupyter Lab. Okay, Phreeqc X1. Okay, that's all. That's everything that you need to do. Okay, so if I type dir, here I have x1.out. Okay, I will change it to the clear theme, because most of you are familiar with the clear theme, so it's better. Okay, so with that, you have run Phreeqc, and then we get the results of Phreeqc. So if we open here, we have the database, we have this, we have the input file, I mean what we have inserted, okay, and then this is the solution composition, molarities, this is the description of this is the physical properties, some redox, and the distribution of the species, and as well as the saturated index. Okay, if you see, there are a lot of numbers here, but we are going to work with the Julia notebook in order to analyze this in a more practical way, because this is a lot of numbers and maybe we don't get a real sense of what is going on with the reaction. Okay, so what do we do here on scripts? I'm going to open a new notebook in Julia. Okay, give me one of these. Okay, so okay, this is as well my first script in Julia, so don't worry if you find it complicated, because for me I find it also complicated. We are going to import the package. Okay, we are going to import the limited files and plots. Okay, take a little bit, and this is kind of difference with Python, for example, because in Python it's much quicker to import a package if you are in the interactive mode. Let's see. I mean, it's not. I mean, let's be open to the development, because there are other things that are faster and there are other things that are slower, and there are other things actually it's not the same. I mean, for me, I also thought that maybe Julia will be another type of Python. Some things are similar, but it works in different ways. Okay? In the end, it works in different ways. So we are going to open the Phreeqc as it opens as an array, and this is very practical. Okay, it opens this as an array, is reading, and it transports as an array. Okay, so this is the this is the slicing. This is the slicing as in Python, and we get for example, for this part, the molarities and the moles of the elements. No? Okay, and then we are going to define some breakers. Why do we need to define some breakers? Because we are going to analyze different parts of the output file. Because, for example, we need to, for distribution, we need to analyze this part to here. Okay, and for saturation, we need to analyze from here to here. And those breakers are the ones that we find with Julia. So with this, we define the parts that work for the solution, for the composition of the solution. Okay, and actually it goes from line 95 to 108. Remember that Julia do not start in 0; it starts on 1. So there is no problem in having like you had in Python, where the first element is number 0. Okay, so we do a slicing just to get the matrix of the solution. Okay, so this is the matrix of the solution. Actually, in the matrix can be some elements can be strings and some elements can be floats. This is very helpful if you want to do something quick, but if you want to do further filtering, maybe you will need to insert a struct element that is an element that we are going to show you later. Okay, and then we can do a plot using the plots file, where we can see which are the we can see on a bar chart which are the most, I mean, on the bar chart, which are the most abundant elements in our solution. Okay, taking some time. I don't know, maybe I can do it faster in another tutorials. Okay, so we have that chloride and sodium are the most common, then some magnesium, some some sulfur and calcium as well, some potassium. Okay, great. Then we are going to analyze the speciation. Okay, so that goes from line 133 to line 275, and here we are going to clip, and then we are going to because if you see here, this is not recognizable as I think that this is an empty value, but this is not recognizable for Julia as a number. So I just inserted as a 0. So what I do here is that I replace this expression as a 0. Okay. And okay, well, it's already been replaced. But for example, we have also the total molarities of the element here, and I don't want this for my species analysis. So what I'm going to do is that I'm going to, here for example, I can plot all the compounds that have carbon inside. So these are all the compounds that have carbon inside, because actually goes from line 4 to line 15. And okay, and I see that the carbon in my system is mostly on bicarbonates and these elements. Okay. And then we have we want to analyze which are the most abundant species. Okay, and for that, what do we do is that we filter all the total molarities of per element. Okay, so actually here there is no carbon here, because actually carbon is not a species. Okay, and then we insert something great that is a extract object. What is extract object? Extract object, structured object, is it's kind of a data frame. Yeah, if you work with Python, it's kind of a data frame. It's an element where you can do where you define that each attribute of the element has to be whether a string, float, integer, or boolean. Okay, so this is a struct, and we need to do structs in order to do the sorting of our. Okay, we create an empty list to store our extract species. This is the empty list, and then we do a loop over this array in order to store in this empty list all of the extracted objects. Okay, I don't know if you follow me this way. It takes some time, okay, but I mean what you have done here is that you have compiled, you get a list of a lot of extracts, objects. Okay, and why? Okay, so we have a list here of all the extracts, and then you tell me, why do I need this? Well, you need this in order to do the filtering. Okay, if we want to filter, we need to filter from this list. So I'm going to sort the species list by the attribute of the molarity. Okay, and then with that we go, and this is the order that is descending, because if ref is false, it's ascending. And then, okay, we see that the most common species in this solution is water. Then comes the ion chloride, the ion of sodium, magnesium +2, sulfate, and so on. Okay, but maybe you need something more. You need to do a graph on that. In order to do a graph on this, what we are going to do is we are going to create some empty list in order to plot. I mean, to capture this filter. We need to capture this filtering in order to plot it. Okay, with this we capture the filter in list. And for example, here what we have is that this is a graph where here is modality, and these are the most common species in water. This is the 10 most common species in water. 9 most common. Yeah, 9 most common species in water. Okay, and then you see on the as related to the column size the amount of moles in the solution. Okay, and then you see, okay, water, chlorine, sodium, magnesium, sulfate, potassium, calcium, and magnesium sulfate and sodium sulfate. Okay, what else do we need? For example, we can plot the modalities, but we can plot also the activity. We can plot the activity, and then we see that the activity is much higher related to water from calcium and sodium. No? And then we are going to work with the saturation index. So from these ones are to identify the breakers, and from 268 to 298 we can do we clip the text just for this part. Okay, we create another mutable object, okay, for the saturations, where we have the saturation index as an attribute, and then we do the filtering in something related to what we have done before also, so there is no problem. And for example, we do a list of struct objects, and from that we can do filtering. We can do filter on this list of struct objects. I run the cells by shift enter, so if for any case you don't see what do I do, so actually I don't do that, so I just type shift enter and it's the same. So this is a filter where we see which are the most common minerals. No, the minerals that are more saturated. Yeah. And then we can see as well, in order to capture this, we create a new list, some empty list. This is more for the plot, and for the plot, these are the most common. This is the most saturated. This is the most saturated minerals. The minerals that are saturated on the solutions, and these are the less saturated minerals. Okay, by the index of saturation. Okay, and then if we see, do you remember that we had it on the exercise a phase of uranite. This phase of uranite is not of the less saturated, is not of the most saturated. Okay, Is only one species in. Ah no, here is is one of the uraninite uraninite is less saturated, so actually more uraninite can be uh, uh, can be is less saturated. So I guess that means that can be diluted more uraninite, and it won't mean that it will precipitate. Okay, so this tutorial of Phreeqc, how to run Phreeqc and how to analyze it with uh, with uh, with Julia. I hope that you like it. This was really interesting for us. This approach to work with Julia. It took me some hours, but for I see some promising things in Julia, and for that analysis, but also to run some finite difference models like for groundwater flow and so on, because actually it works really well with arrays. And in Julia, you don't need to import anything fancy to work with matrix here. Okay, so far this is my tutorial. I hope that you find it useful. And my name is Montoya. Thank you for following Geochemical Labs. I hope to see you in coming tutorials. Bye bye. Bye.